Okay friends, having seen Green's theorem and its applications, now let us come to the Stokes theorem. Imagine a closed curve C which is surrounded by an open surface if P is a point where the unit surface normal is n cap, then the Stokes theorem gives a relation between the line integral over this closed curve and the open surface S. The statement is closed line integral f dot dr is equal to the open surface integration of the curl of f dot n cap ds. So this is nothing but the curl operator. So there is a relation between the open line integral over a closed curve and an open surface integral. Specifically, if the curl of the field is 0, then closed line integral f dot dr would be 0. 2. If curl f dot n cap is some constant lambda, then closed line integral f dot dr would be equal to surface integral lambda ds, which is lambda times the surface area of S. If this surface is a known surface like cylinder or sphere or parallelepiped, then you can estimate the surface area straight away. Otherwise, if the surface is known to be some other surface, then you have to produce this result using actual classical integration. So let us now get into problems on the Stokes theorem. Question number 1. Given the field f is equal to y square I plus xyj minus xzk and C is the boundary of the hemisphere x square plus y square plus z square is equal to a squared, comma z greater than or equal to 0, what is the value of the closed line integral f dot dr? Okay, now this is a closed line integral. If you recall the last lecture, then a closed line integral can be evaluated either by the Green's theorem or the Stokes theorem. The Stokes theorem becomes the automatic choice when the field is a three-dimensional field, that is when it contains the ijk components. That is what we have here. The field contains ijk components, so there is no scope of applying the Green's theorem but the Stokes theorem. And performing this line integral would be cumbersome, so therefore we convert this by Stokes theorem into a surface integration. So let us calculate the curl of f. ijk dou by dou x, dou by dou y, dou by dou z, y square, xy and minus xz. So this would be I times 0 minus 0 minus j times dou by dou x of this is minus z minus 0 plus k times y minus 2y. So this would be zj plus y minus 2y is minus y k. All right. Now remember, we are interested in answer is obtained from curl f dot n cap ds. So this part is already computed, so we need n cap. N cap is a unit surface normal of the given surface. So we'll have to calculate the surface normal of this field, this potential. So suppose you take phi as x squared plus y squared plus z squared minus a squared, then del phi would be 2xi plus 2yj plus 2zk divided by, that is, suppose we take a n cap directly, so we are also dividing by the magnitude, square root of 4x squared plus 4y squared plus 4z squared. So simplification of this would be xi plus yj plus zk by a, because square root of 4 gets cancelled with 2 and square root of x square plus y square plus z squared is nothing but a squared. We get this. So n cap is also available. Now when you take the dot product of del cross f dot n cap, then it would be the dot product of this and this one. So this will be z into y, yz, minus y into z is minus yz by a. So that's a very lucky situation. Del cross f dot n cap has become 0. So if you go back and see, our answer is produced from this step. So this will be surface integral 0 ds. So the answer is 0. So we have escaped real surface integration in this case, because this dot product became 0. But whenever that is not 0, there are two cases. It can be a constant, which is a simpler situation, or whenever it is some function, then serious integration will have to be performed. So the correct option for this problem is A. Let's go to the next question. Question number 2. What is the result of surface integral del cross f dot n cap ds, where S is the surface of the hemisphere, x squared plus y squared plus z squared is equal to 16 above the xy plane, and the field F is equal to x squared plus y minus 4i plus 3xyj plus 2xz plus z squared k. So again, this is an application of the Stokes theorem. The question is to find this, but this is identically equal to closed line integral f dot dr. So we are given this, we will evaluate the right hand side. So now let us take f dot dr. Answer will come from closed line integral f dot dr. This is nothing but closed line integral f1 dx plus f2 dy plus f3 dz. This is nothing but closed line integral. F1 is this x squared plus y minus 4 dx plus 3xy dy, and the third component will be 0 because z is equal to 0 implies dz is equal to 0. So we are left with only this part, and a natural reaction will be apply Green's theorem. This is nothing but double integral dou by dou x of the second component minus dou by dou y of the first component. Dx dy. So this will give us double integral over r 3y minus 1 dx dy. Now what is this region of integration? This region of integration will be to combine these two equations. So when z is made 0, you get a circle x squared plus y squared is equal to 16. So it is a circle with radius 4 units centered at the origin. So you can evaluate this using polar coordinates. So this will be integral 0 to 2 pi 0 to 4 3 into r sin theta minus 1 into r dr d theta. Okay. So you have to just convert this into polar coordinates. Now when you look at the first term, after integration with respect to r, when you integrate with respect to theta, the integration of sin theta over 0 to 2 pi will be 0. So therefore this term can be removed because it does not contribute anything to the answer. So what is left is only the second part. So this is integral 0 to 2 pi 0 to 4 minus r dr d theta. So let us evaluate it because it's a very simple situation. So this will be minus 0 to 2 pi r square by 2 from 0 to 4 d theta. So this will be 16 by 2, that is 8. So this will be minus 8 from 0 to 2 pi d theta. So this will be minus 16 pi. So the correct option for this problem would be B. So what we have done in this problem is, given the open surface integral, we have evaluated through the closed line integral, and the advantage with this problem is because of the non-existent dz term, the possibility of using the Green's theorem became real. So therefore one has to be in very good touch with Green's theorem even while solving problems on Stokes' theorem. That is one real possibility. Let's go to the next question. Question number 3. What is the output of del cross f dot n cap ds surface integration, where the field f is equal to yi plus zj plus xk and s is the surface of the paraboloid, z is equal to 1 minus x square minus y squared with z greater than or equal to 0. So the field f is equal to yi plus zj plus xk. S is the surface of the paraboloid, z is equal to 1 minus x square minus y squared above the xy plane, and the question is, what is del cross f dot n cap ds? So we'll convert this into a line integral f dot dr. So this would be f1 dx plus f2 dy plus f3 dz, but this will become 0 because dz is 0. So this will be closed line integral y dx plus z dy. This is identically equal to double integral over r dou by dou x of z minus dou by dou y of y. This is by Green's theorem. So this would be 0, that would be minus 1. So minus double integral 1 dx dy over r, where the region is x square plus y square less than or equal to 1. So therefore this is nothing but minus area of unit circle. This is equal to minus pi into 1 square, which is minus pi. So the correct option for this problem is B. Once again, we have escaped integration because of this constant times dx dy. If something would come here, then let us not forget that the polar option is always available. Let's go to the next question. Question number 4. What is the output of closed line integral sin z dx minus cos x dy plus sin y dz, where C is a rectangle with limits 0 less than or equal to x less than or equal to pi, 0 less than or equal to y less than or equal to 1, and z is equal to 0. So from the given integral, we can extract the field f is equal to sin z I minus cos x j plus sin y k. And we will be using Stokes' theorem for this problem. It will come from the RHS del cross f dot n cap ds. And here the surface has been mentioned clearly as a rectangle with x is equal to 0, x is equal to pi, y is equal to 0, y is equal to 1 on the plane z is equal to 0. So therefore, n cap is equal to k. N cap is equal to k because the lamina is on the xy plane. So what we need is del cross f, for which we must take the curl of the field. Del cross f is equal to determinant ijk dou by dou x dou by dou y dou by dou z sin z minus cos x and sin y. So this will be I times dou by dou y of sin y is cos y minus 0 minus j times 0 minus cos z plus k times sin x minus 0. So this will be I cos y plus j cos z plus k sin x. So now if you look at this operation, del cross f dot n cap would give us only sin x. Therefore, this would become double integral over r, rather surface integration sin x ds. But this can be converted through the projection formulas into sin x dx dy by magnitude of n dot k. But n dot k is nothing but 1. So therefore this would be double integral over r sin x dx dy. And this is the region of integration. Therefore you can easily perform the integration with limits being constants. So this will be 0 to pi and 0 to 1 sin x dx dy. Integration of sin x from 0 to pi would be 2. So this becomes 2y. From 0 to 1, so it is 2. So the correct option for this problem is C. So this is a problem where the actual curl had to be calculated, and then very importantly the surface normal is n cap is equal to k because the lamina is on the xy plane, and then fortunately for us the integration is still not very challenging. So let's go to the next question. Question number 5. What is the output of surface integral del cross f dot n cap ds, where the field f is equal to x square I plus xyj and s is the square bounded by 0 less than or equal to x less than or equal to a, 0 less than or equal to y less than or equal to a in the xy plane. So here the field is x square I plus xyj and s is the lamina 0 less than or equal to x less than or equal to a, 0 less than or equal to y less than or equal to a in the xy plane. So now the question is to find del cross f dot n cap ds. Let us not forget S is an open surface, of course it's a lamina, so this will be identically equal to closed line integral f dot dr by the Stokes theorem. This is nothing but closed line integral x square dx plus xy dy, and the k component does not exist. So once again we'll go to the Green's theorem, double integral dou by dou x of xy minus dou by dou y of x squared dx dy. This is double integral over r y dx dy. So we'll be forced to integrate. The region of course is very simple. It's a square lamina. X is equal to 0 to x is equal to a, y is equal to 0 to y is equal to a. So those will automatically be the limits of integration. So 0 to a, 0 to a, y dy dx. So this is 0 to a, y square by 2 from 0 to a dx, a square by 2 into x from 0 to a, so that is a cube by 2, and you can see that option A is the correct option. So again here, even though the function is not constant or 0, the integration was not tough because of the region. Now this is where we'll have to practice double integrations carefully, because we are not sure of very simple situations every time. So depending upon the region, then the appropriate decision about double integration should be taken place. When it's circular, get ready for polar. Otherwise, don't forget the Rx and Ry region concepts. So these are 5 problems which generally can be expected in these types of examinations. So overall, if you want to have a better exam, don't forget your basics principles of double and triple integrations, the concepts of Jacobians, and then remembering the correct statements of the Green, Stokes and the divergence theorem. We will now have a small discussion on divergence theorem before attempting a few questions.